Welcome to Math 172, Galois theory. Today we're going to discuss algebraic elements and algebraic extensions. Before we do so, let's review some ideas from before about the basics theory of field extensions. And what follows, let R be an integral domain. Recall that the characteristic of R is that non-negative integer m, which generates the kernel of the map that takes an integer k to the multiplicative identity of R added to itself k times. Since R has no zero divisors, its characteristic must either be 0 or prime p. Hence, either the integers or the finite field Fp must be a subring of R. Let's denote F as the field of fractions of our ring R. Notice that because R is an integral domain, there is an embedding that sends R into its field of fractions F by simply taking an element lowercase r and mapping that to the equivalence class R over 1. Now let's consider the composition that takes the integers into our field of fractions f by sending an integer k to the sum of 1 over 1 to itself k times. By considering this map, we see that the characteristic of f must be the same as the characteristic of r. Hence, either the rational numbers or the finite field of p elements must be a subfield of f. Now let script O be any integral domain that contains R integral domain R, and let's denote K as its field of fractions. Then F must be contained in K. In this case, we say that K is an extension of F, or that F is a base field of K. We'll write K slash F. The following diagram may be useful to keep track of some of the symbols that we've introduced so far. Recall that for any positive integer n, we may have the Cartesian product f to the n, which is simply just a collection of n-dimensional vectors whose coordinates lie in our field of fractions f. Recall that this here is a group under addition. Let's make the following definition. We say that a map phi from Fn into a field K is an F vector space embedding if it satisfies the following three axioms. First, phi of alpha times A must be alpha times phi of A for all scalars alpha and for all vectors A. Second, phi of A plus B must be phi of A plus phi of B. And third, the kernel must be the trivial set. That is, it simply consists of just one element, that is the zero vector, in R space Fn. In this way, we may view Fn as an F vector subspace of K. In fact, we're going to use this to actually view f to the n as a ring. We'll denote the index of k over f as the largest n such that we have such an f vector space embedding for fn into k. We'll also call this the degree of the extension of k over f. Our extension k over f is said to be finite if this index is a finite integer. We prove the following proposition. Say that k over f is a field extension. If we can find a surjective F vector space embedding of Fn to K, then K over F is a finite extension of degree n. Here are a couple of examples. Let's let R be the integers z so that its field of fractions F will be the rational numbers Q. Say that D is an integer which is not a square. We can consider the set K, which we denote by Q adjoint square root of D, as just the set of numbers of the form A plus B radical D, where A and B are rational numbers. Not only is this a field, but actually we have a map from F cross F to K that sends the vector A comma B to the complex number A plus B radical D. This is not only an F linear bijection, but also shows that the index of K over F has to be 2. Using this map, we actually see that there are many ways in which we can turn F2 into a ring. This simply comes from the fact that we do have a multiplicative structure for K. As another example, let's say that L equals R, the real numbers. We can show that L over F is an infinite extension. Indeed, for any positive integer K, we can consider the map that takes an n-dimensional vector to a certain sum, a sub 0 plus a sub 1 theta plus dot 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 a sub n minus 1 theta raised to the n minus 1. We've written down such a map for any real number theta. Well, if we pick a theta, such as maybe the number e, 2.718, or the number pi, 3.14159, then we see that V would have to be an injective map. This means that we have an injective map, that is an F vector space embedding, from Fn into L for all positive integers n. In other words, the extension L over F must be infinite. Today, let's discuss algebraic elements and algebraic extensions. We'd like to explain how to generate field extensions. Let's say that R is an integral domain and let F be its field of fractions. We'll let f of x be a non-constant, monic, irreducible polynomial with coefficients in our integral domain R. First, there exists a field extension k over f so that f of x has a root theta in k. Second, let f parentheses theta be the smallest such field. Then this field must be a quotient f square bracket x mod the ideal generated by lowercase f of x, and the degree of this extension must be the degree of the polynomial f of x. We'll call this extension f parentheses theta a simple extension of f, and we'll say that theta is a primitive element for this extension. Before we prove this proposition, let's make a few remarks. Notice that this proposition states that given a non-constant irreducible polynomial, number one, there exists a field such that this polynomial has a root theta. Number two, the smallest such extension is a finite simple extension of f. And number three, this extension must be a quotient of the form f square bracket x divided by, or I should say modded out by, the polynomial lowercase f of x. Let's go ahead and prove the proposition. We'll begin by showing the first part. Let's denote K as the quotient ring f square bracket x modded out by the polynomial lowercase f of x. Well, f is a field, so the polynomial ring must be a principal ideal domain. Also, by assumption, our polynomial lowercase f of x is irreducible, so the ideal generated by it must be a maximal ideal. Hence, this quotient ring, namely K, must be a field. We'll show now that this field K must be an extension of f where our polynomial has a root theta. Let's consider the map from the polynomial ring to its quotient ring, namely f square bracket x to k, as sending the variable x to simply x mod our maximal ideal P. We're going to let theta be the image of this. That is, theta is simply the coset x mod the maximal ideal P. It's easy to check that f of theta must be 0 mod P, so that theta in our quotient ring K must indeed be a root of our polynomial. It remains to show now that K must be an extension of our field F. Let's take the same map that we had before, and let's consider now the restriction to the field F. In other words, if A is in our field F, then phi of A is simply the coset A mod the maximal ideal P. Notice that if phi of A is 0, then this actually means that A must lie in the maximal ideal, but then actually this shows that our polynomial f of x must divide A. The only way that a polynomial can divide a constant is if that constant is 0. So this shows that this map phi must be an injective map. Hence, by the first isomorphism theorem for rings, we see that the field of fractions f must be isomorphic to f mod the kernel of phi, which must be isomorphic to its image, which is a subfield of K. So this does indeed show that K is an extension of f where our polynomial, lowercase f of x, has a root. Let's show the second part of the proposition. We're going to let K be the smallest field extension of our field F that contains this root theta. We want to prove that K, just like above, must be the quotient ring F square bracket x mod this maximal ideal P. Let's consider a map phi that maps from f square bracket x to k, which is simply the evaluation that sends a variable x to the root theta. It's easy to see, since P is a maximal ideal, that P must be the kernel of this map phi. By the first isomorphism theorem for rings, we see that f square bracket x mod P must be isomorphic to a subfield of K. But the subfield must also contain F and the root theta, so by the minimality of our field K, we must have equality. Let's do the last part. We actually need to compute the degree of this extension and show that it's simply the degree of the polynomial f. Let's write out f as a polynomial of degree n. We'll observe here that the polynomial ring f square bracket x is a Euclidean domain. This means that if we're given any polynomial a of x in the ring, then we can use the Euclidean algorithm to write a of x as q of x times our irreducible polynomial f of x plus some remainder r of x. Notice that r of x at most has degree n minus 1. So this means that if we're given any polynomial a of x that lies in a polynomial ring f of x, then inside of the quotient ring f square bracket x mod the maximal ideal p, then we actually see that every element really must be a polynomial of degree at most n minus 1. This is what you see here on your screen. Let's consider now a surjective map from Fn to this quotient f square bracket x mod p that simply takes an n-dimensional vector a0, a1, dot 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 through an minus 1 to the polynomial a0 plus a1x plus dot 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 an minus 1 x to the n minus 1 mod our maximal ideal p. It's easy to see that such a map must satisfy the additive properties and the F-linear properties that are coming from our axioms. Also, it's easy to see that this map is surjective, so it really suffices to show that here we have a map that is injective. Let's take a look at the kernel. Say that we have a vector b0, b1 through bn minus 1 that is in the kernel. We can form the polynomial g of x from these coefficients. Because it's in the kernel, this must be 0 mod p, which means that the polynomial f of x must divide this polynomial g of x. However, notice that g of x has degree less than the degree of f, so this means that g of x must be identically the zero polynomial. But the only way that this happens is if our original vector b1, b0, b1 through bn minus 1 was just the zero vector. Hence, the kernel must be the trivial subgroup, showing that we really do have a surjective F vector space embedding. So by the proposition we discussed in the previous lesson, we must see that the index here is n. Here's an example. We'd like to explain how we can generate the complex numbers using this previous proposition. We can write C, the complex numbers, as numbers of the form a plus bi, where a and b are real numbers. Let's consider that ring homomorphism that simply takes a polynomial, f of x, and we'll just evaluate I, the square root of minus 1, for x. The kernel here consists of polynomials such that f of I has to be 0. In fact, we see that x squared plus 1 is one such polynomial. However, this is irreducible in R because it has no roots in R, so this means that the kernel of this map must be the ideal generated by x squared plus 1. Of course, we see that this here must be a maximal ideal. And in fact, the quotient ring, namely R square bracket x, modulo this maximal ideal, must be the same as the complex numbers. So this actually gives us a way to think of the complex numbers. We can define it as the quotient ring that consists of R square bracket x modulo the maximal ideal generated by the irreducible polynomial x squared plus 1. Notice that the map phi that we wrote above really doesn't care which root of x squared plus 1 we choose, either plus I or minus I. All that matters is that we find this irreducible polynomial x squared plus 1. So far, we've seen that if we're given a polynomial, we can actually construct an extension K over f that contains a root. Today, we'd like to do the opposite. we'd like to say, let's say that we're given some theta. Can we now construct a field that contains theta? Say that F is a field, and let theta be any element, not necessarily an element that's in F. We have two statements we'd like to show. First, there exists an integral domain, F square bracket theta, and an extension K over F that contains theta. Second, the following four statements are equivalent. First, there's a ring homomorphism, F square bracket X to F square bracket theta, that sends X to theta, which is not injective. Second, there exists a non-constant polynomial, f of x, such that f of theta is 0. Third, there exists a finite extension k over f containing theta. And finally, f square bracket theta is a field. Before we prove this, let's write down a few definitions. More generally, say that theta 1, theta 2, so on and so forth, are a collection of elements. We'll denote k by f parentheses theta 1, theta 2, so on and so forth, as the smallest extension of f that contains each of the theta sub i's. By induction, using proposition 113, such a field exists. We say that an extension k over f is finitely generated if k is in this form for a finite number of elements, theta sub I. Any element satisfying the four equivalent statements in the second part of this proposition is said to be algebraic over f. Otherwise, we say that theta is transcendental over f. Finally, if k over f is an extension, we say that k over f is an algebraic extension if every element theta in k is algebraic over f. Otherwise, we'll say that k over f is a transcendental extension. We'll discuss all of these properties and definitions much more in the future lesson. But for now, let's prove the first of these two statements. Let's consider the following group ring. Here we'd like to consider finite sums where we consider a0 plus a1 theta plus dot dot dot. And let's consider a surjective ring homomorphism that takes the polynomial ring f square bracket x to this group ring R by sending x to theta. Since this polynomial ring is a principal ideal domain, the first isomorphism theorem for rings asserts that this group ring R must be isomorphic to f square bracket x modulo a maximal ideal f sub 1 of x for some polynomial f sub 1. Notice that f sub 1 need not be an irreducible polynomial because we're not given that R is an integral domain, so we have to be a little bit careful here. Let's denote f of x as either 0 if f sub 1 of x is the 0 polynomial, or else pick any irreducible polynomial that divides f sub 1 of x. Now, we can send R to an integral domain. Let's denote f square bracket theta as the polynomial ring modulo now this maximal ideal f of x. We now have a surjective map from R to this integral domain f square bracket theta. Notice that we've written things here so that theta really does lie in f square bracket theta, and also it's a root of this polynomial f of x. In fact, f square bracket theta need not be a ring, so we can simply construct K as this field of fractions. It's an integral domain, so this is perfectly fine. In this case, K over F is the desired extension of F square bracket theta that contains our root theta. Now let's show the second part of the proposition, which gives these four equivalent statements. First, we'll do 1 implies 2. Observe that the map f square bracket x to f square bracket theta that simply sends x to theta, this must have a kernel generated by some polynomial f of x. If this map between these two rings is not injective, then notice that f of x must be a non-constant polynomial where f of theta is 0. Let's do 2 implies 3. Say that there is a non-constant polynomial where f of theta is 0. Since our polynomial ring is a unique factorization domain, let's take our f of x, factor it into irreducibles, And therefore, we know that at least one of the factors, let's say m of x, must satisfy m evaluated at theta is equal to 0. This m of x must be an irreducible polynomial, so let's denote the field, which is the quotient ring, f square bracket x modulo the maximal ideal generated by this irreducible polynomial. Then k over f must be a finite extension containing theta because the degree of k over f is simply the degree of this irreducible polynomial m. Now let's do 3 implies 4. Without loss of generality, let's say that k is the smallest field of f containing our root theta. We know that there must be an embedding from f square bracket theta to f parentheses theta. Remember that f square bracket theta is an integral domain, but f parentheses theta is a field. We see that the map that takes the polynomial ring f square bracket x to f square bracket theta, simply sending x to theta, must have a kernel. Let's say that it's generated by some polynomial f of x. And in this case, we therefore see that f square bracket x must be the same, f square bracket theta must be the same as f square bracket x modulo the maximal ideal generated by this irreducible. Now, we can use all of this to really ask the question, must the extension k over f be finite? Let's assume that it's not finite, and let's see what happens here. That means that we should have, for any integer n, an f vector space embedding where things are going to run into problems. So for example, we can consider fn embedding into f square bracket x, this polynomial ring, and we know that there's always such an embedding. But since f of x equals 0 is the zero polynomial, whenever we plug in x equals theta, then we actually see that there's going to be a slight problem. So the point here is that if we don't have a way to say that f of x is the zero, if f of x is the zero polynomial, then there's actually a problem and the degree of k over f must be infinite. So we see that f of x must be the zero polynomial, and so we're done. Finally, 4 implies 1. Say that f of theta is a field. If we have a surjective map from f of x onto f square bracket theta, if this were also injective, then f of x would be isomorphic to f of theta, would be a field, but we know that this polynomial ring f square bracket x is not a field. This is a contradiction. That concludes the proof. Thanks very much for watching.